Hey folks, sorry this video is going to be a little different than the other ones. I'm having some technical difficulties, so I'm using some slightly different software. But here we go. In this video, the goals are up here. And to get us started, what I'd like to do is to consider the vector field 0x. So we've seen this before. All of the vectors are vertical, since there's no horizontal component to all these, and they get longer as x increases. And we'll consider two line integrals of this vector field. Both will go from the same start point to the same end point, but the first one, C1, is just a line segment that does that. The second, C2, is a quarter circle that does that. And we may have already computed these. If not, I would encourage you to try it on your own, but what we should find is that the line integral of f along C1 is equal to 1/2, while the line integral along f along C2 is pi over 4. So they're both positive. The vector field is helping us move along each of these paths, but this second is more positive. That is, we're getting more help from the vector field as we move along this semicircular path. So we'll keep this example in mind when we do some definitions. So the first definition is that of a path-independent vector field F. So we say that a vector field is path-independent if, well, when we start with any points in the domain, and then any path from the first to the second of those points, then our vector field will be path independent if the line integral of f is the same along both those paths. So another way to say that is that the only thing that matters is the start point and the end point. Let me finish this definition. It's that the line integral of f along C is equal to the line integral of f along D. So in other words, only the endpoints matter. And what's left if a vector field is not independent, path independent, well then that's the definition of a path-dependent vector field. If you take in discrete math or vector spaces, there's a little bit of logic going on here. We don't have to get into it, but path independence is a for all statement or for any statement. So the negation of that is a there exists statement. So there is at least some pair of points and there's at least some pair of points, let's call them P and Q, with paths C and D from P to Q, so two different paths, where the line integrals are not the same. And well, this first example we did, this is an example of a vector field that is path dependent. That is, it's not path independent. We saw here that by choosing to travel along C1 versus C2, we got a different answer. So, for example, the vector field 0x is path dependent. Proving path independence is a lot harder because it's a statement about every pair of points and every path between those points. So we can't just try some examples and see if it works. We'll see. We'll get to something a lot nicer. You can read about this in the book. A path-independent vector field is sometimes called a conservative vector field, and that comes from physics, from conservation of energy. One more example before we move on. Well, what can we say about a circulation integral? Remember, this symbol is a circulation integral, that little circle around the integral sign, which just means that C is a closed path. So we can imagine C as just a loop. Well, if C is just a loop, then the start point P and the end point Q coincide. And if our vector field F is path independent, it doesn't matter how we get from P to Q. The answer should be the same. Well, one way we can get from P to Q is the lazy path, that is, not move at all. And, well, if we certainly don't move at all, we can't get any help from the vector field, or physically speaking, the vector field, a force field, is not doing any work to move us. So your intuition is right if it's telling you that the integral of a vector field along a lazy path, or a constant path that's not moving, should be 0. And that's just as good as any other path in a path-independent vector field. So we'll conclude that if F is path-independent or conservative, then a circulation integral, every circulation integral, should be 0. And we'll come back to this, and this will be important in what's coming next when we talk about Green's theorem. So what we're building up to is a fundamental theorem of calculus, but let's start by thinking about the old fundamental theorem. Specifically, this is probably what your teacher or professor called the second fundamental theorem of calculus, or FTC Part 2. So this is the Calc 1 FTC. It says that we could take the difference between endpoints of an interval, probably start in the opposite direction, but this is fine. And that difference should be equivalent to the integral of the derivative. And I'm sure that the last time you saw this, it wasn't in terms of a derivative, it was in terms of an antiderivative, right? The integral of this function, we can evaluate it by taking the antiderivative and plugging in the endpoints. But I hope you'll agree this is the same. What we've got here is, on the left side, the net change in F between the endpoints, and on the right side we're taking the integral of a rate of change. So keep that in mind as I tell you about the fundamental theorem of calculus for line integrals.